questions 21 through 25 on the 2020 grade 12 AMC 12B. How many positive integers n satisfy n plus 1,000 over 70 is equal to square root of n bracket? Recall that bracket x is the greatest integer not exceeding x. Notice something really quick, that if root n is the root of a perfect square, so for example, if n is a perfect square, so something like k squared, then root n would be obviously an integer. So if you took the bracket of it, it would just end up being the same as root n. The bracket doesn't change it because you're dealing with an integer. So if you do that really quickly, you can substitute that into this equation, and you get n plus 1,000 cross multiply 70 root n. Square both sides and you get n squared plus 2,000 n plus 1,000 squared is equal to 70 squared times n. And if you bring everything on one side, you get n squared plus, this is going to be 2,000 minus 70 squared, and that's the coefficient for n, and then just 1,000 squared is equal to 0. So that becomes n squared minus 2,900 when you do that math, plus 1,000 squared. And then this factors very nicely, actually. You get n and 400, 2,500, negative, negative. So immediately you get n equal to 400 and 2,500. Great. Now, what if n is not a perfect square? I had said it's a perfect square. What if it's not? So what if n is not simply k squared, but there's some additional, fractional, or not actually fractional, but some additional number. So that's a bit abstract, so let me explain what I mean. Let's say k is equal to 6, right? When n was equal to k squared, then that was simple. It's just 36, which is a perfect square, as I'm sure you know. But now I'm saying it's not a perfect square. It's something plus j. So at this point, it would be 36 plus j. Now 36 plus j cannot be a perfect square. Otherwise, we're right back to this whole scenario again. And the only way it will not be a perfect square is a special condition, and that j has got to be either greater than or equal to 0 or less than or equal to 2k. And that's very important. It's very interesting, actually. So, for example, in this case, we have k to be 6. So j would be less than or equal to 12. Because watch what happens when j is greater than, when it's outside of this boundary, let's say it's 13, and we add it to 36, it becomes 49. And 49 is a perfect square. So it goes right back to this scenario. So we can't make it a perfect square again, and that's why we have to have this very all-important boundary, or range, I should say. All right, so hopefully that makes sense. So now, since we have set n is equal to k squared plus j, we have to figure out what is root n bracket. Well, that's going to be k squared plus j root and bracket. And that is pretty much going to be the same as k, because once you take the bracket, you drop the decimal part of it, and you just get the number. So this now we put back into our original equation, and off we go. So that would make me have the following: n plus 1,000 over 70 is equal to k. So cross multiply and you get m plus 1,000 is equal to 70k. And then now n is this, so I got to substitute that in. So that's k squared plus j plus 1,000 is equal to 70k. I'm going to isolate for j. So that's going to give me minus k squared plus 70k minus 1,000. And we can factor this if you really want. It's going to be k minus 20 and k minus 50. Okay. Now, j is this, right? But we have a very nice range for j. So I can put that j into that range. So j is between 0 and 2k. So it's between 0 and 2k. But j is this. So minus k squared plus 70k minus 1,000 is between 2k and 0. All right. So let's take this one step at a time. Let's look at that one first, and then I'll look at that one. Okay. So this one, I'll do it over here. I don't like that minus k squared, so I'm going to multiply through by negative 1. And when I do, I get k squared minus 70k plus 1,000. When you multiply through by negative 1, the sign reverses. So this becomes the other way around. So it would be less than or equal to 0 like that. If I did that correctly. And I believe I did. So now this factors. So k, 50, 20, and negative, negative. So if this was a parabola, it is a parabola that opens upwards, and we want it to be less than 0, that means it's got to be this region right here. So that means k has to be less than 50 or greater than 20. And I guess it's equal to also, because it's less than or equal to. Okay, that takes care of that part. Pretty decent. Now let's do this one. This one, multiply through by negative 1 to get minus 70k plus 1,000. Switch the sign, minus 2k. And then add 2k to both sides, and we get minus 68k plus 1,000 is less than or equal to, greater than or equal to 0. Okay, unfortunately, this one involves a quadratic. It doesn't factor that nicely. So you do this quadratic, and you're not allowed to use a calculator, so we have to approximate now. Unfortunately, we've got to do a quadratic and approximate what the number will be. And when you do, you get 46.5 approximately and 21.5 approximately. So this is actually another parabola, of course, that opens upwards, but this time we want it to be greater than 0, so we've got to have this segment and that segment. So that means k has to be either greater than 46.5 or k has to be less than 21.5. Okay, so we have to combine this with this to get values for k. And it looks like the only integer values for k are k equal to 20, 21, and then 47, 48, 49, and 50. And for each k, you're going to get one value of n, because n is equal to k squared plus j. So if there are 6 values for k, there'll be 6 values for n. And they don't want you to figure out what those values are. They just want you to figure out how many. But just for the case of for the sake of completion, if you want to figure out n, you can. K you already have up here. J you can get with this formula right there. Just plug in values of k into there to get j, and then you'll be able to get your values of n. Not that you need to, but if you really want to during your practice, then the values of n would be 400, 470, 22, 90, 23, 60, 24, 30, and 2500. And at the very beginning, I had gotten those two. So 6 values, and therefore, number 24, the answer is C. What is the maximum value of 2 to the power of t minus 3t all multiplied by t over 4 to the power of t for real values of t? I am going to make one substitution, and that is going to be let x equal t over 2 to the power of t. And in a careful way, I will show you how that substitution will be placed into our equation. Our equation is 2 to the power of t, 3t, all multiplied by t, all over 4 to the power of t. So the first thing, of course, I can just break this up. This is 2 to the power of t multiplied by t over 4t. And then 3t squared over 4 to the power of t, like that. And we want to eventually find the maximum value. So now we can break this up. I'll just do this on the side. 4 to the power of t is really 2 to the power of 2 to the power of t, which is 2 to the power of 2t. And that can also be written as 2 to the power of t squared if needed. So that's what I'll do. I'll write it as 2 to the power of t, 2 to the power of t all squared. And this part is going to be 3t squared over 2 to the power of t squared. Okay, now things start to cancel out. The 2t, one of them cancels from the numerator, and all you're left with is just 2 to the power of t. Now this part, the 3 I'll put out front, but the t and the 2 to the power of t, we can combine that as a squared like that. Now I'm ready to put in my substitution. And the x was t over 2 to the power of t. So that's just x, and that is just 3x squared. Very nice, right? At this point, if you want to find the maximum, you most definitely can. And you do that by completing the square. Now, first of all, this equation, if it was, say, y is equal to, it's a parabola, right? And it's a parabola that obviously points downward because the coefficient in front of the x squared is negative. So it's kind of like this. So obviously there will be some maximum point. And we have to figure out when is that. For what value of x is that maximum point, and what is that maximum point? Okay, and we do that by completing the square. And I am sure you know how to complete the square, so let's talk about that. First, let's factor out the 3. That's going to give me x squared minus x over 3. Now what I have to do is I have to take half of this coefficient in front of the x and square it. So the coefficient is negative a third. So I have to take half of that, which is negative a sixth, and then square it, which would become 1 over 36. So that's the process of completing the square. So I add 1 over 36, and then I subtract 1 over 36. Because if you add something, you have to subtract it. You can't change the equation. Okay, now what happens is this part beautifully factors out. And that's the whole point of completing the square. X minus 1 over 6 all squared. And then before we kick this out of the bracket, we've got to multiply it by that negative 3. So don't forget about that. So that's going to be 3 over 36, which is 1 over 12. So that means, going back to this little graph, x, when it equals 1 over 6, the maximum value of this is y is equal to 1/12. When x equals 1 over 6, this whole thing vanishes. It just becomes 0. And what you're left with is 1 over 12, which is the max. So there we go. Very nice question. Number 22, the answer is C. How many integers n greater than or equal to 2 are there, such that whenever z1, z2, until zn are complex numbers such that the magnitude of z1 equals the magnitude of z2, equals the magnitude of zn is equal to 1, and z1 plus z2 all the way till zn is equal to 0, then the numbers z1, z2, zn are equally spaced on the unit circle in the complex plane. Well, let's go through the cases one by one, because there is no actual formula to do this. We just have to churn this out case by case. All right, so when n equals 2, what is the scenario? First, let's draw a little coordinate plane. Nothing fancy is needed. And let's draw that unit circle that they talk about right here. So, a unit circle. Okay. So, when n is 2, you only have two values, right? We have z1 and z2. So the first criteria, which is right here, and then the second criteria we have to fulfill, and then the third criteria is that they are equally spaced. So 3 criteria must be all fulfilled. So the first criteria is that the magnitude of Z1 is equal to the magnitude of Z2. Okay, that's fine, is equal to 1. So both of these are 1. I'll put 1 here, so that's Z1. And I'll put Z2, I'll put it there. And I think that should work. So first criteria is satisfied. Second criteria is that when you add them up, it equals 0. Well, this is equal to just 1. We haven't even gone on the imaginary axis yet. We're just staying on the x-axis. This is negative 1. So Z1 plus Z2 is 1 minus 1, and that is 0. Okay, second criteria, check. Now the third criteria is that they're equally spaced. Are they equally spaced? And the answer is yes. The number of degrees from there to there is 180. The number of degrees from there to there is 180. So the third criteria, equally spaced, is satisfied. So therefore, n can equal 2. So far we have one value. They want you to figure out how many values, how many integers, n greater than or equal to 2 are all these criteria satisfied. Now we move to n equals 3. So again, same sort of strategy here. We're going to draw a brief basic unit circle and off we go. Okay, the three values, Z1, Z2, Z3, I've got to make them all equal to 1 in terms of their magnitudes, right? So I think that shouldn't be a problem. It's a unit circle, so I can just put 1 here. That'll be Z1. And then I'm going to try to, now I've got to make them equally spaced, right? Well, that's easy. There's 3, the whole thing is 360, so 360 divided by 3 is 120. All right, so approximately there, and approximately there. I'm going a little out of order. I should be talking about that first, but I jumped to that. Doesn't really matter. As long as I meet all 3. The order shouldn't matter. Okay, now, equally spaced. Yeah, I made it in a way that it's equally spaced. So each of these would be 120. This is 120 degrees. This is 120 degrees. And this is 120 degrees. All right, great. So that's checked. Now, what is the third criteria? Right, I've got to make sure that they all add up. Z1 plus Z2 plus Z3 have to equal 0. Can I do that? Well, in this case, it's a fairly, I hesitate to use the word easy because, people get offended when you say easy, but relatively straightforward question at this point because we've got a triangle, if this was drawn to scale, that will help us figure out what are the coordinates. Well, this Z1 is easy. That's just 1. But what's Z2? The magnitude is 1, but what is the actual complex number? Well, that was 120 degrees, right? So that means this here is 60 degrees. This is a right angle the way I've drawn it, and therefore that's 30 degrees. So again, for the 1000th time on a math contest, we have a 30, 60, 90 triangle. And the ratios, of course, I'll write it up here. I mean, by now, you should definitely know this. 60, 30. The ratio is 2, 1, root 3. So since this is 1, that means based on that ratio, this will be a half, and this will be root 3 over 2. All right? So z, in terms of its complex number coordinate, is minus root 3 over 2 plus 1, or sorry, minus a half, because that's the real part, minus a half plus root 3 over 2i. Okay, z3 is minus a half, that's the x part, plus minus root 3 over 2i. Okay, let's add them up. Z1 is 1, Z2 minus a half plus root 3 over 2i. Z3 minus a half minus root 3 over 2i. And what does this equal? Well, 1 minus a half, and then plus root 3 over 2i minus root 3 over 2i, and that is equal to 0. There you go. N equals 3 works. Okay, moving right along, let's do the exact same thing now for n equals 4 and see what happens. So let's just change things up a bit. Okay, we've got now our unit circle again. And now we've got n equals 4. N equals 4, again, I've got my criteria that all of these have 1 in terms of their magnitude. That's easy. You can just draw the radius 4 times anywhere. Okay? And there's 1, here's 2. Okay, that's fine. And then 3 and 4, is there any way to make them equally spaced? Well, let's talk about the z1 plus z2, the sum first. And I think we'll get to the equally spaced part later. If I can make 4 of these add up to 0, well, this is 1 and this is negative 1, so that satisfies z1 and z2. Okay, that's good. And if I put any 2 points diametrically opposite, like if this is z3 and this is z4, then the sum will be 0. For example, if you notice, this and this will have the same sort of lengths. They would just be opposite. It would be x plus yi, but z4 would basically be minus x minus yi, since they're diametrically opposite from each other. So indeed, this will hold true. But notice, when you do that, they're not equally spaced. The distance from here to here, I don't know, it's maybe 60. But then the distance from here to here is certainly not 60. It's greater than 90. So not equally spaced. Not equally spaced. So that means that n equals 4 is not possible. And similarly, the same story would hold true for any even number. By the same principle, you can show exactly what I showed for any even integer, 6, 8, and so on. Okay, so now all we are left with is n equals 5 and all odd. N equals 5 and all odd. So all odd n greater than or equal to 5. All right, so let's see what happens in this final scenario. And there we go. We've got a unit circle. Okay, so now I've got 5 z's, and that criteria can be easily fulfilled. And they just draw 5 lines that are length 1. And then, but I've got to make sure that z1 plus z2 plus z3 plus z4 is equal to 0. Well, I'm going to actually combine the n equals 3 scenario. If you look back, I had created a beautiful scenario for n equals 3, where this was z1, this was z2, and this was z3. And I had shown that up here, right? This was n equals 3. And I shown that when you do it like that, you can make it work. It will be equally spaced, and all of these will add up to 0. So this is going to be 0. I've already shown that. Now all I have to do is choose 2 that add up to 0, and that can be easily done. Just choose 2 that are diametrically opposite from each other. So let's just choose that, I guess. Top and bottom. So this is z4 and this is z5. z4 is, since it's on the imaginary, it will be plus I, and z5 it will be minus I. So this will also add up to 0, so this criteria is checked. But my final criteria, which is the equally spaced one, notice it is not. Because this is obviously 90. This is, I don't know, maybe 20 or 30. This is 60 maybe. 60. I think it was 60 if I recall. And this is 30 and this is 90. So they're not equally spaced. And the same story holds true for any odd n greater than or equal to 7. Or n greater than or equal to 5. All right, so we've done it. I think it's a challenging question. Some people are saying on the internet that this is easy. I don't think it's easy. All right, number 23. In any case, the answer is B. Let d and n denote the number of ways of writing the positive integer n as a product n equals f1 times f2 dot 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 fk, where k is greater than or equal to 1. The f at I are integers strictly greater than 1, and the order in which the factors are listed matters. That is, two representations that differ only in the order of the factors are counted as distinct. For example, the number 6 can be written as 6 times 2 times 6, or 2 times 3, and 3 times 2. So D6 would be 3. 1, 2, 3. What is D96? Okay, I wanted to give a little bit of a primer before I jump right into this question. And that is, how do we figure this out? Well, they gave us a nice example that D6 is 3. And they even showed us how. D6 is 3 because 6 can be represented as 6, or 2 times 3, or 3 times 2. And that is the only way I can break it up into a string of numbers where the product is equal to 6. So since there's only 3 ways of doing that, D6 is 3. All right, now I want to see, is there a relationship between different D's? So for example, if I have D12, can I write that as a relationship with other D's? Let's see. What is D12, for example? We can figure that out pretty quickly. It can be either 12 by itself, or it can be, let's see here, 4 times 3, 3 times 4, 2 times 6, 6 times 2, and I think that exhausts when k is 1, it's like this, but when k is 2, I think these are the only 4. And when k is 3, meaning you have 3 numbers, I think the only way is just all the prime factors, which is 2 times 2 times 3. So we have 1, 2, 3, 4, 5, 6. So are there any more? There should be. I see. This has iterations. 2 times 3 times 2, 3 times 2 times 2. Because they even tell me that in the question. Two representations that differ only in the order of the factors are counted as distinct. Okay, so that's why. So 1, 2, 3, 4, 5, 6, 7, 8. I got 8. So D12 is 8. Now, when you fiddle around with this, you hopefully will be able to conclude that D12 can be represented as the sum of the D's of its factors. So D6, what are the factors of 12? 6, 4, 3, 2. Right? 1 they don't want because they want F1 to be greater than 1. Okay, no problem. Now, D6 is 3. D4, I can easily figure that out. D4, I can either represent 4 as 4 or 2 times 2. So D4, there's only 2 representations, so D4 is 2. D3 is just a prime number, so there's only one way of writing it, and that's just 3. So D3 is 1. And D2 is also a prime number, so there's only one way of writing it, and that's just 2. Okay, 1, 2, 3, 4, 5, 6, 7. Ooh, 7. But the answer is 8. Well, here's the thing. You have to add one more. Why? Because that final one represents just the 12. This one right here. When it's by itself. That's why we have to add that one. So, it is indeed 1, 2, 3, 4, 5, 6, 7, 8. So, which is what we got. So, that's an important sort of conclusion to come to in this question. A bit challenging, I think. I do not think it's easy, especially when you have like 2 minutes on a math contest. All right, so what do they want us to figure out in this question? D96 right here. Okay, so I will do D96, and off we go. So D96, as we have previously concluded, will be a sum of the D's of the factors of 96, which are 48, plus 32, plus 24 plus 16 plus D12 plus D8 plus D6 plus D4 plus D3 plus D2. And as previously mentioned, we have to add on a 1 at the end because that represents the representation of 96 when we have just one number. All right. So here we go. Some of these we already know, right? D2 is 1, D3 is 1, D4 we had calculated as 2, D6 we had calculated as 3. So now we have to figure out all the other ones. Okay, so D8, well, that, in a very similar way, you just break it down instead of doing it the long way. D4 plus D2 plus plus 1. Remember, you have to put the 1 at the end. Don't forget that. So this is going to be just 2 plus 1 plus 1. And that is 4. So D8, put a 4 there. And now we have D12. And D12 is D6. D12 actually we just did. Yeah, we just did D12. So that was 8. Okay. I don't need to go through that whole thing then. It's just 8. So I did that in the primer. Great. So that's 8 right there. All right, moving right along. What's next here? D16. Okay, so D16 with our same sort of philosophy is the sum of the D's of the factors. So D8, D4 plus D2 plus that 1 at the end. So that's going to be 4 plus 2 plus 1 plus 1, and that is equal to 8. So D16 is 8. All right. So I think you get the hang of this. D24, that is going to be D12 plus D8 plus D6 plus D4 plus D3 plus D2 plus 1. And these numbers are 8, 4, 3, 2, 1, 1, and 1, and that is equal to 20. All right, so we got 2 more. Let's squeeze it in on the same page. So D32 is D16 plus D8 plus D4 plus D2, and then don't forget that 1 at the end. And this is going to be 8 plus 4 plus 2 plus 1 plus 1, and that is 16. So we are almost done. And then I just have to figure out D48, which is going to be D24 plus D16 plus D12 plus D8 plus D6 plus D4 plus D3 plus D2, and then don't forget that 1 at the end. And all of these guys added up, this is what D24 was 20, D16 is 8, and then D12 is 8, and then we have plus 4 plus 3 plus 2 plus 1 plus 1 plus 1, and that is equal to 48. Okay, that was the last piece of the puzzle, 48. All right, so now I just have to add up these guys, and when I do, I get 112, and that is the value for D96. So number 25, the answer is A. For each real number a with a between 0 and 1 inclusive, let numbers x and y be chosen independently at random from the intervals 0a and 0,1 respectively, and let p at a be the probability that sine of pi x squared plus sine of pi y squared is greater than 1. What is the maximum value of pa? So we have sine of pi x all squared plus the sine of pi y all squared. And that is greater than 1. So what I'm going to do is look at the boundary first, and then we'll talk about the greater than. So the boundary would be the 1. Now, we know from our trig identity that 1 can be written as sine squared anything plus cos squared anything. So I will write it as sine squared pi x plus cos squared pi x. That's one of the more commonly remembered trig identities of the many, many identities. So that means this cancels with that, and all you're left with is sine squared pi y is equal to cos squared pi x. We still don't have the same variable. Now we get into one of the lesser known trig identities, and that is as follows. This can be written as follows. It can be written as sine squared pi 1/2 plus or minus x. So that is one of the more lesser known. So for example, that is going to be equal to sine squared pi y. So for example, if x was 1, then cos squared pi would be equal to -1 squared, which is 1. So that would mean cos squared pi times 1, and that's going to be just 1. And then you plugged it into here, it would become, well, for either one, it would give you, say, if x is 1, it would be, if you use the positive, it would be 3/2 times pi, which is 270. Sine of 270 is -1, and when you square it, it becomes, again, 1. So that's when we have 3/2. And then if you use the negative, this guy right here, it would be 1/2 minus 1, which is -1/2. And -1/2 of 180 degrees is -90. And the sine of that is also -1. When you square it, it's a 1. So I just wanted to show you that this identity definitely does work. And I think that's one of the harder identities to remember. But nevertheless, here we go. Well, now that we have that, we can equate. That means pi y is equal to pi 1/2 plus or minus x. And this gives me two equations. It gives me pi y is equal to pi 1/2 plus x. And it gives me pi y is equal to pi 1/2 minus x. So drop the pi's, and this gives you 1/2 plus x. That's a nice equation. Drop the pi's here, and we get 1/2 minus x. Again, a very nice equation to work with. But we have more solutions, because if you took the square root of both sides, you would have a situation where you'd have taking the square root of both sides, we'd have sine of pi y is equal to minus sine of pi. I initially just did the plus, right? But now we also have to do the minus, because that's going to give me another. Well, again, we use another one of those trig identities that if you have this out front, like here, you can put it inside. So it would be the sine of minus pi, and then the rest is the same, like that. Okay, so now this will give me a couple more, I think. I have this line and this line so far. This, if I equate that, it's going to be pi y is equal to minus pi 1/2 plus x. And then the other one would be pi y is equal to minus pi 1/2 minus x. Drop the pi's and I get y is equal to minus 1/2 minus x. Drop the pi's here and I get y is equal to minus 1/2 plus x. Okay, great. Now I take those four equations that are just lines, and I will plot them Initially, I'll plot them exactly the way they are, and then I have to translate them, and I'll explain all that. So plotting these are easy. When x is 0, we have a half, and then when x is negative a half, you have 0, and so on, right? So you can easily plot those 4 lines, and when you do, and you combine them, you get a shape that looks like this. Now, I have to now shift the graph to match our boundaries. I have to shift to the unit square. Now you say, well, what are you talking about, unit square? Well, let me draw the unit square first, and then I'll talk about it. So here is my unit square. Now, where did this unit square come from? Well, it came directly from the question. You see, the intervals of x are chosen from 0 to a, but a is between 0 and 1, and then y is chosen from 0 to 1. So that is where the unit square comes from. So for example, I'll write it out here. X is chosen from the interval 0 to a, and y is chosen from the interval 0 to 1. So this is x, and this is y. Well, y is from 0 to 1, so this is 0 to 1. So y is definitely all the way from there to there. There's no discrepancy there. But x is from 0 to a. But a, they're telling me, is anywhere between 1 to 0. I don't know what the value of a is. It's somewhere between 0 and 1. So a could be here, a could be here. I don't know. So let's just leave that alone. But one thing we do know is that the maximum that a could be is 1. And the minimum is 0. So the range for a is between 0 and 1. Now what we have to do is we have to translate that. We have to shift that to match here, because our boundaries are 0 to 1 on the x-axis and 0 to 1 on the y-axis. So we have to shift the graph to match our boundaries. Okay, and that's not a problem. I can just draw that same shape here, and hopefully it'll be somewhat accurate like that. Okay, there we go. Now we have to start talking about that P at A, that whole thing that they were discussing. P at A is the probability that that equation happens, the probability that this is greater than 1. Now it will be greater than 1 if it has values inside the shape. So if you don't believe me, we can look at this. It's sine squared pi x plus cos squared pi y, and we want it to be greater than 1. Well, it's got to be inside that shape. Let's test it out, because either it's inside or outside, right? So let's just test out some point inside this. I'll just say that is xy is a quarter, and then y is 0. And let's see what happens to this equation. When we have x equal to a quarter, it's going to be the sine squared of 180 divided by 445, and then 0, so cos squared is 0. Well, sine of 45 is 1 over root 2, so if you square it, you get a half. And the cos of 0, well, you know that is 1. So when you square that, it's 1. And 1 plus a half is 3 over 2, and of course that is indeed greater than 1. So that means points got to be inside. So that's just something I wanted to show to illustrate that we now are working with this unit square, and in particular points that are inside. So now we have to talk about the probability that P at A. We have to maximize this P at A. Well, what is P at A? It's the probability that something lies inside this shape that is surrounded by green, so some point in there, divided by the total region for some value of A. Okay, so let me illustrate. Let's say my A is here, and I don't know what the value of A is, but I've just put it there. And then therefore, what is my region? Well, my region therefore is just going to be until that point. So my region, if that is where A is, my total region is this total area. And like any probability question, the total goes in the denominator. So what's the area of that total? Well, from here to here is A. From here to here is 1. So it's a rectangle with the dimensions A times 1. Now the numerator is our specific condition, and that is that it's got to be within that boundary. So I've got to figure out the area of that in terms of A. Now, there's two scenarios. The first scenario is that the way I drew it right now, that A is greater than a half. So if this is a half, it's on that right side of the half. The other scenario is if A is less than a half, less than or equal to a half. And that's, of course, when A would be here, let's say. So I've got to figure out the probability for both and compare them and then proceed with the maximum. Okay, so it doesn't really matter. Let's do the A less than a half first. So if A is less than a half, it's something like this, right? Where this is my value of A. Okay, so let's figure that out. P at A, therefore, would be as follows. It would be the area of the total, which I have already illustrated was A plus 1. That's just a rectangle. And then the area this time of that triangle. So that triangle, if we draw that line, that's like, representing an altitude. 1/2 base times height. The base is from here to here, and the height is from here to here. Well, the height is easy. That's just A. And the base, well, here's the thing. This is an altitude, so that's 90. And then the shape was giving me 45-degree angles. If you looked at those original lines, the slopes were all 1. So those are 45-degree angles. So that means this is 45 degrees, and this is 45 degrees. So that means that this is an isosceles triangle. So from here to here is the same as from there to there. Since that is A, this is A, and therefore that's A. So the base is 2A. So that just gives me A squared over A. And that's just A. And A is less than a half. So less than a half. So when A is less than a half, the probability is less than a half. All right? We want to maximize the probability. So let's see what happens when A is greater than a half. When A is greater than a half, now I've got to do pretty much the same thing. But this time, I have to look at a slightly different set of shapes. The total probability, again, is that rectangle. That's not going to change, so that's just A times 1. But now the numerator, that is a little bit different. That numerator now is this guy right here. You see that? And I'm going to break that up into 2. So I've got the triangle, this guy, and then I've got a trapezoid right here. So keep that in mind. So triangle, I'll just write that here, triangle plus trapezoid. So we are going to need some space, so I'll write that over here. And that's going to be all over A. Okay, so now let's carefully figure out this area. Triangle and trapezoid. Okay, triangle should be easy. That's 1/2 base times height. So 1/2 base, well, the base is all the way top to bottom. That's just 1. The height is from here to here. That's just a half. So as I said, the triangle part is easy. Trapezoid is a little bit more complicated. First of all, do you know how to figure out the area of a trapezoid? Here's the trapezoid. If this is A, this is B, this is the height. The area of a trapezoid is A plus B divided by 2 times the height. So this trapezoid, this is my first length, that's just 1. This is my second length. Okay, I got to figure out that second length. So I've got to do a little bit of brainstorming here. Let's figure this out now. All right, so what is this distance from there to there? Be careful. It's not A. It's A minus a half. This distance. So A minus a half. Now, previously, I had gone through the angles. This is 45 and this is 45. So that means this is the same as that. So this distance is also A minus a half. And you can do the same sort of story up there to show that that is A minus a half. So this distance would be the full top to bottom, which is 1, minus 2 of those A minus a half. So that's just going to be 1 minus 2A plus 1. So that's 2 minus 2A. All right. So plus 2 minus 2A all over 2, and then multiply by the height. The height is from here to here, and that is A minus a half. All right. This is the equation we have to simplify and maximize. So here we go. So this is going to be a quarter, and then when we multiply this out, we're going to have plus, it looks like 3 minus 2A over 2. And then this will be A minus 1 half. And then the A, I can immediately just invert and multiply to make this 4A and 2A. Might as well just put it in there. So now this will be 1 over 4A, and then multiply this out. I'm going to put the 1 over 2A out here and just multiply what's remaining. So that's going to be 3A minus 3 over 2 minus 2A squared plus, it looks like A. Okay, so we've got 1 over 4A, and then now let's use the multiplication of the fraction. So that's going to give me just 3 over 2 minus 3 over 4A, and then this looks like just minus A, and that's just plus a half. All right, great. So adding all the like terms, it looks like a minus A plus 2 minus 2 over 4A, and that is minus A plus 2 minus 1 over 2A. All right, great. So that means that's 2 minus A plus 1 over 2A. And this is our P at A, and this is something we need to maximize. Well, at this point, it's going to be maximized when this is the minimum, right? The smaller this is, the bigger this whole thing will be. So now I'm going to concentrate on minimizing that part. So to minimize that, I've got two sums. So this is where I have to use AMGM, arithmetic mean, geometric mean. And some of you may remember, an arithmetic mean of two numbers is A plus B divided by 2, the average. Geometric mean of two numbers is given by A times B, square root. And the arithmetic mean, AM, is always greater than or equal to the geometric mean. And if I multiply through by 2, you can write it as A plus B is equal to 2 times AB. So this is used on math contests, not very commonly, but can be used. So now compare this to this. This is also a sum of two things. So that means A plus 1 over 2A would be greater than or equal to. This is my A, so, well, that's just A. This is my B now, so I'll put that here, 1 over 2A. So A plus 1 over 2A is greater than or equal to, well, the A's cancel and you just get 1 over root 2. And therefore, that is going to be, that's just root 2, right? 2 divided by root 2 is root 2. So that means that A plus 1 over 2A is greater than or equal to root 2. So the smallest possible value is root 2. So the minimum possible value of that is root 2, so that's what I'm going to put in. And that gives me my maximum possible value of P at A. And before I circle that as an answer, I have to do one final step, is that compare it to this, because remember that was the probability I got when a was less than a half. And when I compare less than a half to 2 minus root 2, this is of course the maximum of those two. So 2 minus root 2 is the answer to this very challenging question, number 25, and that would be choice B.